So today we're starting lesson 10, which is El Niño and La Niña. We are still in module 1. We're going to be talking about gyres, which are surface currents in the ocean that are deflected by Coriolis. So remember Coriolis force from the pressure chapter. This also affects ocean currents. So in our case, the Gulf Stream is nearby. It's in the east coast of the United States and is strengthened by westerly winds and continues northeastward, which I'll show you in a minute. And so just a reminder that waves and surface currents are wind generated. So you see the direction of the waves and the currents are going to be determined by where the wind is coming from. So why is this important? When it comes to our global winds and ocean currents, the heat exchange that occurs in storms when water evaporates from the surface is actually a very important role in keeping the overall planet balanced. So hurricanes are a big part of this. We covered those last time, where the water vapor is carried away, it's borrowed from the ocean, and then it's later released into the atmosphere. So oceans actually contribute more than 2/3 of the heat balance between the mid-latitudes for the atmosphere, and that's quite a bit. So we live here in the magical balance land, and so at the equator, that's 0 here, there's a surplus of heat energy, and what happens is these hurricanes and these storms actually transfer that surplus into the deficit zones, which are here in the higher latitudes. And there's definitely a connection between the sea and the atmosphere. We see that the sea and the air are connected to each other. They're influenced by each other. They have the same kind of dynamics occurring in each other because both are fluids. They're different densities, but they're both fluids, and the sea is 1,000 times more dense than the air is. We see here that the Pacific Ocean actually will contribute to that heating and cooling more than any other ocean. Notice that the Arctic and Antarctic oceans are missing here. We're only talking about Indian, Atlantic, and Pacific. So Pacific is definitely the biggest one. It's a big bathtub, and so it definitely has a huge influence on the overall planet. And we're going to see one of those influences in this chapter. So here are surface currents, and we see the gyre that I would like you to learn is the North Atlantic gyre. So we see the Gulf Stream again coming from the Gulf of Mexico up the east coast of the United States. Then it becomes something called the North Atlantic Drift, and that goes into roughly where England is. And so that's why England is generally warm climate, not super warm, but if we go directly across, it would be the same as Newfoundland, and they get lots of snow, and England does not. So this warm ocean current is actually keeping them from getting colder than they would be. And then to replace all this, because we can't have any vacuum, we have upwelling that occurs. We'll get to what that is in a minute, along the west coast of Africa, right here, near the Canary Islands. So it's called the Canary Current. So it's a blue current because it's cold. Red is warm, by the way. So here comes the cold water to replace it. And then we have warm water at the equator, which is called the North Equatorial Current. So the whole thing is called the North Atlantic Gyre. Other things to note here, that on the west coast of continents, generally speaking, you will see cold currents, right? So Peru, California, Canary, over here in Africa, I'm not going to butcher that name. And then on the east coast of continents, we see warm currents. So we see the Gulf Stream, Brazil current, and then the ones over here. Notice Australia has its own thing kind of happening. So anyway, you see that both in the northern and southern hemisphere, we do have these gyres, but the one in the northern hemisphere turns clockwise, right, because of Coriolis, and then in the southern hemisphere it goes the opposite. Now, why is this important? That would be because ocean currents actually have a big impact on climate. Besides what I've already told you with that heat balance, it also affects the local area as well. So a warm current produces this warm, moist climate a little bit more than usual because of that nearby water source. And then the same is true the opposite way. Cold currents will chill the air, which means it increases aridity, or it dries out the air. So as my bucket size decreases, right, there's less humidity that the air can hold because the cold doesn't let you hold as much moisture, basically. And this is a picture of the Atacama Desert, which is the driest desert in the world. It's in Chile. And we know that this is next to the Peru Current, which is a cold current. So what is upwelling? I talked about it before, mentioned it before. Now we're going to talk about it. So upwelling is a wind-induced vertical movement. It is the rising of cold water from deeper layers to replace warmer surface water. So here you see in the picture that the surface winds are being pushed away from an area, right? So if I'm pushing something away, I now have a vacuum that I need to replace, so it comes up from below. And you might know that as you go deeper into the water, it's going to be colder, so I'm bringing colder water up to replace the warmer surface water. And so this occurs where winds blow parallel to the coast towards the equator. So it's blowing parallel, it bumps into the coast, it turns, and then that upwelling occurs to replace that water. And this tends to be colder and nutrient rich, which is good for our fishies. So the fishies like it because then they get lots of food, which is good. Okay, so here's another view of upwelling. So you see some whales here, a shark, and then some fish. You see as it bumps into the coast, cold water comes up, warm water is moving away. The overall wind is this way, parallel to the coast. And I asked you in class, have you ever experienced a difference in ocean currents? Even just looking at Florida Atlantic versus the Gulf side, you can see temperatures have a difference here. Let's go in May. You see like Miami is 81, but in general it's going to be in the 70s, and then the Gulf is going to be in the 80s. So we see like there's a difference there. The Gulf is a smaller space, it can warm up more, so it's going to be warmer than the Atlantic side. Okay, so now we move to talk about El Nino. So this picture is from space, and it's of sea surface temperatures, the ocean temperature at the surface, and we see a big red blob right off the coast of South America. Right, here's Central America, here's South America. So this is what we call El Nino. This is the gradual warming of eastern Pacific waters in December or January. It comes from Spanish, it means boy child or the Christ child. It was named by fishermen in Ecuador and Peru who noticed a warm ocean current periodically around Christmas time, hence the little tree I put here. And so what it does is it prevents those nutrient-rich waters from coming up, so there's less fish, which means that the fishermen would take a break, repair their equipment, spend more time with their families. Sounds great, but if it's long-lasting, like more than 6 months, then it leads to economic disruptions, which we'll get to in a minute. So strong El Niños can raise water temperatures by as much as 5 to 10 degrees, which is a lot, in a huge area, extending from the Central Pacific to the west coast of South America, so roughly here all the way to here. We see in this picture, this graph really of ocean temperatures from the 1998 Super El Nino, as I'm going to call it. Really, really strong signal here. Lots of hot water. Also, 1983, which is not pictured, had 2,000 lives lost and over 13 billion in damages just from this warming of this hot water. So that can be from various things, which we'll see later what kind of impacts the El Nino will have. So even a weak El Nino of 2 to 4 degrees can influence the atmosphere. And what it does is it sets up a very strong subtropical jet stream for us. These are surface temperature differences. So there's like a normal, and then I subtract it from what it is, and then it gives me this departure from normal. So you see here that it's definitely more red than normal, meaning it's warmer than normal. I just wanted to revisit and review the jet stream in case you've forgotten from a couple weeks ago. Jet streams are fast streams of air embedded in the westerlies. It's like a tube of air. It's pretty wide, not very deep, and it has wind speeds of almost 300 miles per hour. And we can look at today's So if I go here, up to 300 millibars, then we see this is the current jet stream setup. So as of today, when I'm recording this on October 8th, we see the polar jet stream is kind of doing something weird up here, and then there's the subtropical jet stream. So pretty strong. They might be getting some storms down here. So usually you'll have both, and then in the winter one disappears. So the subtropical jet stream is semi-permanent. Like I said, sometimes it goes away. It's centered on 25 degrees north and south, and it's slower than the polar jet stream, but not when it comes to El Nino. And it contributes to our cyclone development, which will be important when we come to impacts. So if it's in a meridional flow, then it has lots of time for these jet streaks to form and then influence our surface flow that's been developing, as opposed to a zonal flow where we have fast moving systems, one after another. Might not be as strong, but you can get lots of storms from that. Okay. So in El Nino, this is the setup, and we see a strong low pressure that appears in the North Pacific. Now it's always there, but during El Nino it kind of shifts further south, which leads to this flooding, rain, and massive surf to the west coast. Right? So there's a wet kind of blob here that's been circled in green. That kind of indicates where it's going to be wetter than normal. They also get floods and tornadoes in the lower Midwest, and we end up having balmy winters in the Northeast United States. So notice that the polar jet stream is kind of moved northward. Remember I told you that's like the fence where the cold air can come south. So if it's being blocked up kind of in Canada, we don't get any cold weather, so it ends up being a mild winter. Also can deflect hurricanes from northern paths, which we'll see a little bit later. So before we go into abnormal conditions, let's find out what normal is. So the normal trade winds look like this. We have the Peru current here, existing, doing its thing, and we have a general circulation like this. So the winds move from the east to the west across the equator, and it leads to a buildup of warmer water kind of in the western Pacific. Not too much, just a little bit. That's the normal setup. So these are twin belts of steady winds at 23.5 degrees north and south, and they were very popular for sailing vessels, so they called it the trade winds. So during El Nino, the pressure differences across the Pacific changes. So we have higher pressure that builds over here, and it builds in the western Pacific, right? Now, because of the pressure gradient force, which we learned in the pressure chapter, trade winds will weaken, or they can even reverse their flow, which is pretty crazy. So here I have to move from high to low, so this will lead to weak trade winds, or again, cancel them out completely and then go the other way. The warmer surface water is then pushed eastward. So remember, normal was over here, so now I'm pushing that water over here. It bumps into the South American coast and it travels southwards, which then suppresses the Peru current, so I don't have as much upwelling happening. And my sea surface temperatures, that's what SST is, change from the mid 70s to the mid 80s. That's like a lot. Big difference. So thermal expansion leads to an increase in sea level of almost a foot in the eastern Pacific. So here the water gets deeper, and then over here it actually shrinks. Pretty crazy. So how do I get rid of this thing? So after several months, the warm subtropical high pressure will weaken because it's now in contact with a surface that's cooler than normal. So that water is going to be cooler than normal, so it actually causes the whole thing to break apart, which is kind of ironic. But anyway, then my water levels will return to normal. The warm surface water will return back westward to where it belongs, and the water temperatures will drop along Peru and Ecuador back to normal. So this back and forth pattern is called El Niño Southern Oscillation, which is ENSO for short. And so I show you here the kind of pattern of El Nino versus La Nina, which we'll get to a little bit later. So we see that there's red patterns, which are El Nino, as opposed to La Nina, which is when there's colder than normal sea surface temperatures. So those are blue, and we see it kind of has this like seesaw pattern, back and forth, where they balance each other out. So the extreme examples I want to tell you about are 1982-83 and 97-98. So you see I've labeled them here with an orange arrow. These were both extreme. The sea surface temperatures were more than 10 degrees or more above normal. Each appeared in the springtime, and west of the international date line, that's what that means, the wind shifted and came out of the west. So again, it broke down that eastern flow and moved completely the opposite direction. By autumn, our sea levels rose 1 foot as far east as Ecuador and dropped in the western Pacific. So many coral reefs were exposed. They're not supposed to be exposed, so that's bad. And it peaked in January, but by the late spring, early summer, it finally reversed back to normal. So that's good. So why did the fish go away? You might be wondering. Well, the water bulges up as well as down because of something called continuity. It's kind of like if you squish a peanut butter and jelly sandwich, then the stuff in the middle will go out the sides, right? So this is the same kind of idea. If I squish down with warm water, then the cold water has to go somewhere else, right? So El Nino actually leads to subsidence in the ocean. So just like we talked about subsidence in the air, the same thing applies in the ocean. Therefore, we have sinking nutrients and a less amount of nutrients because it's not being replaced from below. So the fish don't have any food, which is bad, which leads to heavy losses in our nearby fishing industries. The anchovy harvest has been known to fail, and sardines vanish. Seabirds that are dependent on fish for their food also relocate because they're hungry. And in 1983's El Nino, it actually devastated the local sea lion and seal population. So sea lion, and that's a seal. Notice the puppy eyes. Okay. Just to show you the difference. Now, it also led to the damage of coral reefs in the Galapagos, which is on the eastern side. So pretty interesting how it can have very far-reaching effects. So what I ask you in class is, can you think of another possible impact of El Nino? So here, this is from, I believe, Australia, and they talk about how we have direct impacts like increased rains on the one side, right? So flooding, storms, cyclones, and then on the drier side with that high pressure, you see drought, wildfires, lack of crops, right? So that leads to malnutrition, food insecurity, diseases, decreased water supply, lack of sanitation, and air pollution becomes a problem because of the fires. So then we see respiratory diseases, reduced access to healthcare, etc., etc. Then on the water side, you see injuries, fatalities from the flooding, increased vectors which lead to vector-borne diseases like malaria. We have waterborne diseases, contaminated water, damaged infrastructure, etc., etc. So there's very wide-reaching impact from this kind of situation. Okay, so let's talk about the Super El Nino, as I'm going to call it, the 1997-98 strong El Nino. It was the strongest on record so far. So I'm going to go through each region. So the Western Pacific, including Southeast Asia, Indonesia, Australia, and Japan, all experienced very severe droughts, and it may have had an impact on Asian stock markets. So there was a plunge of stock market in Asia, could be related to this drought, maybe. That's why there's a question mark. There are extreme fires in Indonesia, over 1 million acres burned, which led to all this pollution. So these are fires here. You can see lots and lots of smoke associated with them. Japan was also hosting the Winter Games at the time, and at first they had not enough snow, and then they had too much snow. So we see here some kind of facility buried in snow. And that high pressure actually trapped those conditions of air pollution, which created this perfect disaster, right? So now I have high air pollution levels. I have it being trapped at the surface, which leads to, unfortunately, fatalities. All right, if we move to California, that's the west coast of the United States, they saw rough seas, flooding and mudslides. The shift in the jet stream led to endless low pressure systems, one after another, which we call training in meteorology. So, like cars on a train track. And this larger temperature contrast, because we have big bathtub of hot water versus the poles, means that these were stronger low pressure systems. We have wave heights of up to 30 feet. I tried to get one for you. This one said it was 30 feet. I'm not totally sure that's accurate, but you get the idea. Big waves. Railroads washed away. Major highways collapsed and turned into rivers of mud, like the top picture. In February, 22 inches of rain fell in San Marcos Pass near Santa Barbara, 12 inches in Ventura, and 3 feet of snow in the local mountains. And all of this lasted until the spring. Doesn't sound like a good time for California. Unusual hurricane events, so I'm going to talk about the Pacific Ocean first. So they actually made landfall this year. Now, I know when we were talking about the hurricanes, we didn't talk about the Pacific because they generally don't make landfall. This time they did. So first we had in fall 1997 Hurricane Nora. So that's this one right here. Nora made a right turn and went right into Yuma, Arizona. Poured tons of rain. And then Hurricane Pauline a little bit later. Acapulco, Mexico. So there's her right there. And that was her track. And these were both Category 4 storms. So pretty strong, getting all that moisture and energy from the big bathtub full of hot water. There's also a Hurricane Linda down here. And she set the record for the strongest storm on record at the time with 190 mile per hour winds. Yikes. Now, in South America, this was directly impacted right next to where El Nino was occurring. We had flooding in Peru and Ecuador, with hundreds of millions of dollars being lost. This disaster actually led to social and political destabilization. The Ecuadorian president was replaced. I guess they blamed them for what was happening. Yikes. 22,000 people were evacuated from their homes during the peak of El Nino because flooding. And on the other coast, the other side, Brazil was hit by a really bad drought, which reached record proportions. So there was 10 million people affected. More than 50% of crops were lost in the poorest regions, which led to looting. That's not a good situation. Then we have the northern United States. So this is the warmest on record, complete lack of wintry weather. Cherry blossoms started blooming in January, which is not normally. Usually it's like April or May. April or March, sorry. And then in New England, they had crocuses going strong by February. No snowfall in New York City. It was called the Year of No Winter in the Mid-Atlantic. And the Quebec, New England got hit by the worst ice storm in the region's history. Travel was paralyzed. Here's a picture of it. Millions lost power for obvious reasons. And it's widely regarded as the worst ice storm in history. Moving southward, we have that subtropical jet stream that's set up. So snow actually fell in Guadalajara, Mexico, which is right here if you don't know. So kind of the middle bottom of Mexico, right? And Roswell, New Mexico, this bottom picture actually got, this is the snow falling in Guadalajara, Mexico. So people seeing this picture might be like, oh, that's Canada. It's not Canada, that's Mexico. Super unusual. Now, back to Roswell. These hunters got stranded because they actually experienced their heaviest 1 month snowfall since 1893 at the time, which was 21 inches. From Texas to Florida, there was tornadoes, including an outbreak that killed 30 people plus in Kissimmee, Florida. And there was that temperature contrast again with upward motion. Plus the jet stream set up some pretty strong storms this year. Ironically, it reversed with the weakening El Nino. So then instead of getting all these storms, they had blistering heat, drought, and then fires in Mexico, which then led to the smoke pouring into Texas. So it was just not a great year for them. Then if we go to the Atlantic Basin, we saw record numbers in the Pacific. So here's the Eastern Pacific, and this is the Western Pacific. You see not so many over here, but just like so many in the Western Pacific. Just a lot of storms. Each of these little colored lines is a storm track. That's nuts. Now in the Atlantic, it was 30% below normal. Here's the Atlantic. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's like 9 or 10 storms. This is the first time in 20th century that the Atlantic passed August without developing a single tropical storm. Pretty impressive. So, if we were in class, I would ask you which of the impacts surprised you the most. This one came from Australia, so we see there's a lot of different impacts. We had East Africans going without food. The rainy season in southern Africa was 50 days late. A lot of people in Latin America had to be relocated because of flooding, but in Ethiopia there was drought. A lot of cows actually died due to hunger or thirst in this drought. There were 6 million tons of maize that were imported into South Africa because they had no crops, 80,000 hungry people, and 9 to 24 months was the duration of this El Nino. So just a lot of different things. Even though this water is over here, it affects the entire world. So the opposite of El Nino is called La Niña. This is the colder than normal ocean temperatures occurring in the same area. So this is when warm water shifts back to the Western Pacific. The deeper, colder water then reaches the surface in the Eastern Pacific, so the Peru Current resumes, and this cold portion of ENSO is called La Niña, or the little girl. So a strong El Nino is frequently, but not always, followed by a strong La Niña. During the spring of 1998, the cold water of La Niña surfaced in a matter of days after the El Nino had dissipated, and the weather patterns almost instantly responded, which is kind of impressive. So recall, this is the Peru Current. This is the Peru Current going crazy. This is what La Niña is. So after that Western Pacific high pressure diminishes, normal flow will resume. So we get that east to west flow at the tropics, and the warm surface water goes back where it belongs. Oops. And so we get a stronger equatorial current and stronger trade winds. So they get even more warmer and then wetter conditions here. Okay, so the extreme example here was 1998's La Niña. During the first 4 months of 1998, record warm temperatures, but it quickly shifted, right? So the El Nino died off, and then it was replaced by this La Niña. So there was a polar air mass that began pushing southward. So now that fence is allowed to move south, we get colder temperatures. We see that snow fell during June in New England. That's not normal. And storms started occurring with great frequency across the northeast United States, and June precipitation amounts were 3 times above normal. And this is kind of what a La Niña looks like. We see colder temperatures in the eastern Pacific, and then that departure from normal, we see all that blue right there, indicating the La Niña. So this is its setup. Through July, most of the Northeast failed to experience a single heat wave. A heat wave is, again, 90-degree plus weather for at least 3 days or more. So no 90-degree days this year. As soon as the subtropical jet stream weakened, right, so that one went away, we see the polar jet stream drop south into the northern United States. Another example, the winter of 1995-96 was the snowiest on record at the time, which was also during the La Niña. There was severe cold in California, and there was the disastrous citrus freeze caused by $600 million in damage. So it caused that. And that was in Florida, and I happen to remember this because our family was really big on orange juice, and that year it spiked to like $8 or $9 a gallon. We bought it by the gallon, so it was like really expensive. And the Midwest got record snowfall with the Arctic blast, because here's the cold bubble that came south, and so you see all these areas got cold and then lots of wet. Okay, so what is the southern oscillation? This is the seesaw pattern of the atmosphere and its pressure between the eastern and western Pacific. So we see here that they've been colorized, this southern oscillation index, with red for El Nino events and blue for La Nina events. So we see that as it departs into the positive, it becomes an El Nino, and when it goes to negative, it became a La Nina event. These also show a cycle between El Ninos or La Ninas of 3 to 5 years. And those things that we saw around the world connecting to the different events is called a teleconnection. So this is weather occurring in a widely separated region in the globe, which you see on this map. So we kind of already covered this, but we see like even in Africa, it can get wetter than normal during El Ninos of the winter time, right? Well, our winter, their summer. And El Ninos that form in the summer northern hemisphere are going to make it drier in this region of the world. Again, notice that this is where the El Nino is forming, and this is where the impacts are being felt. So that's called a teleconnection. For La Nina, we see wetter and cooler conditions generally around the world, which is what we expect with colder water temperatures. And then if it's La Nina during the summertime in the northern hemisphere, we get cool and wet here, which if this happens during their monsoon, it's like really, really, really bad. So very bad situation. So we would watch this in class. It's a rescue situation of floods in 2011, which, if you go back here, you can see was during a La Nina event. Okay, so why do we care about this? Let's go to DC, right? So I have DC and Baltimore. They did this little tally research here of the average temperatures during El Nino winters. Okay, so weak El Nino winters actually lead to below normal temperatures, which you see here. Normal is the dashed line, and then even in Baltimore, dashed line below normal during a weak El Nino. During a strong El Nino, we get above normal temperatures, which is what we expect. So strong El Nino above normal and above normal in Baltimore. When it comes to precipitation, again, dashed line is normal. We see weak El Ninos lead to below normal precipitation here as well, and then strong El Ninos lead to above normal precipitation. So we see strong, above normal, and above normal. And snowfall, the part we really care about, maybe, on average, the stronger the El Nino episode, the warmer and wetter the winters will be. So if it's warmer, then that means I'm going to have less snow, right? Because it's warmer. Now, seasonal snowfall averaged above normal during a moderate El Nino. So not the strongest, but the moderate had above normal snowfall. So there's normal snowfall, 15.4 inches, and we had 26.9 during El Nino winters on average. And then Baltimore gets even more. So normal snowfall of 20.1 during a moderate El Nino 35. So, just saying, El Nino might be good for snow if it's moderate. So there's your vocabulary. And then if we were in class, you would make a forecast based on the current conditions. And so let me go check that out. So if you go to the Climate Prediction Center, they have a discussion of the current status. So this was October 4th, so that was this week. Scrolling down, it says that we're currently under a La Nina watch, meaning that right now neutral ENSO conditions are present, but the sea surface temperatures are near to below average across the Pacific Ocean. So they think there's an 80% chance of a La Nina forming in the winter of 2021-2022. So we'll see what happens. Should be exciting. All right, I hope you enjoyed La Nina. I can talk. And I'll see you next time.